I don't think people understand the significance of a 2,200-year-old computer discovered at the bottom of the sea, a metal alloy that scientists still can't replicate, ancient underground tunnels with perfect ventilation systems. These aren't sci-fi inventions, they're real artifacts that challenge everything we thought we knew about our ancestors. What if I told you that the historical timeline we've all been taught is fundamentally flawed? The Antikythera Mechanism, an ancient Greek device with precision gears that wouldn't be matched until the 19th century, isn't an anomaly. It's evidence of a technological sophistication that history books have failed to acknowledge. Today, we're examining the artifacts that force us to question. Were ancient civilizations far more advanced than we've been led to believe? In 1900, sponge divers working off the coast of the Greek island Antikythera made an unexpected discovery. Among the wreckage of a Roman-era ship, they recovered a heavily corroded bronze object about the size of a shoebox. Initially dismissed as a simple navigational tool, this artifact would later be recognized as one of the most sophisticated mechanical devices from the ancient world. When researchers cleaned and examined the object, they found an intricate system of interlocking bronze gears. The surviving fragments contained 30 precisely cut gears, with tooth counts ranging from 15 to 223. Analysis of the device's structure suggests it originally contained at least 37 gears. This level of mechanical complexity had no known parallel until the development of mechanical clocks in medieval Europe nearly 1,000 years later. For decades, scholars believed the Antikythera mechanism functioned primarily as a solar calendar. However, a 2023 study published in the Horological Journal challenged this assumption. A team led by astrophysicist Graham Wone used advanced X-ray imaging and surface analysis techniques to re-examine the device's calendar ring. Their findings indicate the mechanism tracked lunar cycles with remarkable accuracy, accounting for the Moon's elliptical orbit through an epicyclic gear system. The front face of the device displayed a rotating dial showing the solar year and zodiac constellations with separate pointers, tracking the positions of the Sun and Moon. The back contained two spiral dials, one predicting lunar and solar eclipses, the other likely displaying the positions of the 5 known planets. The mechanism could calculate the timing of future celestial events by turning a hand crank, which moved the gear trains at precise ratios corresponding to astronomical cycles. What makes this device extraordinary isn't just its complexity, but the knowledge required to design it. The gear ratios correspond to known Greek astronomical theories, particularly the work of Hipparchus on lunar motion. The mechanism's creators understood that the Moon's speed varies during its orbit, a concept modern astronomy explains through elliptical orbits. They replicated this non-uniform motion mechanically using a pin and slot system in the gears. The precision of the Antikythera mechanism's components matches that of 19th century mechanical clocks. The gears were cut from a single sheet of bronze using hand tools, with tooth spacing accurate to within a fraction of a millimeter. This raises questions about why such advanced technology disappeared for centuries before reappearing in medieval Europe. Some researchers suggest the device wasn't unique, but it may have been part of a tradition of mechanical computation that was lost during the decline of Greek civilization. This is going to blow your mind. While the pyramids showcase ancient Egypt's engineering prowess, a 2022 discovery at Buto reveals their astronomical knowledge was even more advanced. Archaeologists uncovered the first known Egyptian observatory dating to the 6th century BC, a complex spanning 9,150 square feet with specialized structures for celestial observation. The site contained an L-shaped mud brick building, a slanted stone sundial, and a merkit, an ancient timekeeping device used to track star movements. These instruments allowed precise measurement of solar positions throughout the year. The observatory's layout broke from traditional temple designs. It featured 3 entrance pillars and 2 facing pylons that framed a circular observation area. This configuration created sightlines for tracking the sun's path. An inscribed stone found on site depicted detailed astronomical views across 3 seasons, showing systematic recording of celestial events. The markings indicate observations continued for multiple years, allowing priests to predict seasonal changes. Hossam Ghonim, director of Kafr el-Sheikh Antiquities, stated the findings shattered our expectations. The precision of the instruments and structures exceeds what historians believed possible for this period. The sundial could determine sunrise, noon, and sunset within minutes, while the Merkit measured star positions to track nighttime hours. Such accuracy was crucial for maintaining Egypt's solar calendar, which governed planting cycles and religious festivals. The calendar divided the year into 365 days, with 12 30-day months plus 5 extra days. This system remained accurate because priests used the observatory to correct discrepancies caused by Earth's orbit. They recognized that the solar year wasn't exactly 365 days, a realization modern science attributes to the 0.25-day difference we now compensate for with leap years. The Egyptians adjusted their calendar through direct observation rather than mathematical calculation. Why are there not more people talking about Damascus steel? Around 300 BC, Indian metal workers developed a steel alloy that modern metallurgists still can't perfectly reproduce. Known as Damascus steel, this material began as Wootz ingots from southern India, containing unusually high carbon content, between 1 to 2% compared to modern steel's typical 0.8%. The forging process created distinctive wavy patterns visible on the steel surface. These weren't merely decorative, they revealed the blade's internal crystalline structure. The patterns formed through repeated heating, folding and hammering of the metal at precise temperatures between 650 to 850 degrees Celsius. This process distributed carbon unevenly through the steel, creating alternating bands of hard and soft material. Damascus blades exhibited properties that seem contradictory in modern metallurgy. They maintained razor-sharp edges longer than contemporary high-carbon steels, while remaining flexible enough to withstand heavy impacts without shattering. Microscopic analysis shows the edges developed micro-serrations during use that actually improved cutting performance over time. The blades could reportedly slice through silk scarves dropped onto them and retain their edge after cutting through bone. Recent studies using electron microscopes revealed why these blades performed so exceptionally. The steel contains carbon nanotubes, cylindrical carbon molecules 50,000 times thinner than human hair. These nanostructures formed accidentally during the forging process when trace elements like vanadium and molybdenum in the original Wootz ingots interacted with carbon under specific heating conditions. The nanotubes reinforced the steel's crystalline structure at the molecular level. The exact techniques for producing true Damascus steel disappeared in the 15th century. The Mongol invasion led by Tamerlane displaced approximately 150,000 craftsmen from Damascus to Samarkand in 1401. Later, Ottoman Sultan Selim I relocated more metal workers to Turkey in 1517. These disruptions broke the chain of knowledge transmission. By the 17th century, no smiths remained who understood the full process. Modern attempts to recreate Damascus steel often fail to match the original's properties. Researchers have identified several critical factors in the ancient method. The unique composition of Indian Wootz ingots containing trace impurities, precise temperature control during forging, and specific hammering techniques that aligned the steel's crystalline structure. Even slight variations in these parameters produce inferior results. Contemporary manufacturers use alternative methods to simulate Damascus steel's appearance. Pattern-welded steel involves folding and forge welding different alloys together. Powder metallurgy techniques allow precise control over material composition. Companies like Damascus Steel employ advanced lamination processes to create consistent patterns. While these modern versions achieve visual similarity, they lack the nanostructures and performance characteristics of historical Damascus steel. In the arid regions of the Middle East, ancient engineers developed a water transport system that still functions today. Qanats are underground channels that move water from mountain aquifers to valleys using only gravity. These systems first appeared in Persia around 1000 BC and later spread across North Africa, the Middle East, and even to Spain and China. Workers dug them entirely by hand, with some qanats stretching over 50 kilometers underground. The engineering precision of qanats is remarkable. Builders maintained a consistent slope of about 1 meter per kilometer, just enough to keep water flowing without causing erosion. This required careful surveying using simple tools like weighted strings and sighting rods. The main tunnel would start at a water source, usually a mountain spring or aquifer, then run underground to its destination. Vertical shafts were dug every 20 to 50 meters along the route, serving multiple purposes. These shafts provided access for maintenance, allowed soil removal during construction, and marked the tunnel's path above ground. Majid Labaf-Kaneki, a professor in archaeohydrology, describes qanats as a lifestyle. Building and maintaining them required entire communities to work together. Villagers would organize work parties to clear silt from tunnels and repair collapsed sections. The systems created a shared water resource that supported agriculture in otherwise uninhabitable regions. Some qanats in Iran have operated continuously for over 2,000 years, supplying water to the same communities that built them. The ventilation system in qanats was equally sophisticated. The vertical shafts created natural air currents that prevented dangerous gas buildup underground. Cooler air would enter through the lower shafts while warmer air exited through higher ones. This passive ventilation kept oxygen levels safe for workers maintaining the tunnels. Ancient miners used similar principles in their underground operations, creating airflow through carefully placed openings at different elevations. Modern engineers are rediscovering qanat technology for contemporary uses. The Kartuja Qanat project in Seville adapts the ancient design to cool urban spaces. Workers dug a channel 20 meters underground to circulate water with vertical vents directing cool air upward. The system reduces ground temperatures by 6 to 7 degrees Celsius across an area the size of 2 soccer fields. This demonstrates how ancient solutions can address modern problems like urban heat islands. Qanats also influenced later water systems. The Romans adopted the technology after encountering it in Persia, calling them canales subterranei. Similar systems appeared in China's Turpan Basin and the Atacama Desert of Chile. Standing in Delhi's Qutub Minar complex, a 7-meter iron pillar has defied corrosion for over 1,600 years. Dating to approximately 400 AD during India's Gupta Empire, this 6.4-ton structure represents one of metallurgy's most enduring mysteries. Unlike modern steel structures that show visible rust within decades, the pillar's surface remains largely intact, despite exposure to monsoons and pollution. The pillar's resistance stems from its unique chemical composition. Modern analysis reveals it contains 0.1% carbon, 0.25% silicon, 0.05% manganese, 0.25% phosphorus, and only 0.005% sulfur. This high phosphorus, low sulfur combination creates a protective passive layer just 50 to 100 nanometers thick. When exposed to moisture, this layer forms iron-hydrogen phosphate hydrate, which prevents further oxidation. The same humidity that accelerates rusting in modern steel actually strengthens the pillar's protective coating. Ancient Indian metalworkers achieved this through a sophisticated forging process. They likely heated iron ore with charcoal in bloomery furnaces reaching 1,200 degrees Celsius, then hammered the resulting mass while hot. The repeated folding and hammering removed slag inclusions and distributed phosphorus evenly through the metal. This process created a wrought iron material with superior corrosion resistance compared to modern steel alloys. The pillar's inscription confirms this was no accident. The text describes it as standing as long as the sun and moon endure. Other ancient Indian iron artifacts show similar corrosion resistance, suggesting this was a developed technology rather than a lucky accident. The Dar iron pillar in Madhya Pradesh and iron beams in the Konark Sun Temple demonstrate comparable durability. Archaeometallurgists note these artifacts share the same high phosphorus content and slag-free microstructure. This indicates the technique was standardized across different regions and time periods. Modern attempts to replicate the pillar's properties have yielded partial success. Researchers at IIT Kanpur created samples matching the pillar's composition, but their corrosion resistance didn't equal the original. The missing factor appears to be the specific forging technique. Ancient smiths likely worked the metal at precise temperatures between 700 and 900 degrees Celsius, creating optimal conditions for phosphorus distribution. Contemporary metallurgists struggled to achieve the same uniformity without modern equipment. The pillar's inscription remains clearly legible after 16 centuries, a feat no modern steel structure could match. The Brahmi script names King Chandragupta II and describes his military victories. This preservation provides direct evidence of the metal's durability. Most iron artifacts from this period exist only as rusted fragments. The contrast between the pillar and modern steel structures is stark. The Eiffel Tower requires complete repainting every 7 years to prevent corrosion. In 1936, German archaeologist Wilhelm König discovered a collection of unusual artifacts near Baghdad. These objects, dating to the Parthian period around 200 BC, consisted of 13-centimeter tall clay jars containing a copper cylinder and an iron rod. The copper cylinder, made from a rolled sheet, measured about 5 inches long and 1.5 inches in diameter. The iron rod, inserted through an asphalt stopper, extended into the center of the copper cylinder without touching it. This configuration creates the basic components of an electrochemical cell, two dissimilar metals separated by an electrolyte. When filled with an acidic solution like vinegar or grape juice, replicas of these devices produce between 0.5 volt and 2 volts of electricity. While this output seems minimal today, it could have powered small-scale applications. Experiments show that connecting several jars in series increases the voltage output. In 1978, Egyptologist Arne Eggebrecht created a replica using 10 jars that generated enough current to electroplate a silver statuette with gold. This demonstration suggested one possible use for the original artifacts. The intended purpose remains controversial among researchers. Some propose medical applications, noting that ancient Greek and Roman texts describe using electric fish to treat pain. The 1st century AD Roman physician Scribonius Largus recommended standing on an electric fish to relieve gout symptoms. If ancient peoples understood electricity's numbing effects, they might have developed the Baghdad battery for similar therapeutic purposes. Others suggest religious uses. The mild shock could have created mystical experiences during rituals. Skeptics argue the jars may have simply held sacred scrolls. The asphalt seal would have protected papyrus or parchment from moisture. However, corrosion patterns on the iron rods show signs of electrochemical reaction rather than simple rusting. X-ray fluorescence analysis reveals copper salts on the inner surfaces, consistent with electrolyte leakage. These findings support the battery theory more strongly than the scroll storage hypothesis. The technology appears isolated to Mesopotamia during the Parthian era. No similar devices have been found in other contemporary cultures. This singularity raises questions about whether the jars represent an intentional invention or accidental discovery. The components, clay pots, copper and iron, were common materials used for various purposes. Some researchers suggest a metalsmith might have noticed the electrical properties while working with these materials in liquid solutions. If confirmed as batteries, these artifacts predate Alessandro Volta's first modern battery by nearly 2,000 years. They represent a technological path not taken, an early understanding of electricity that never developed into wider applications. The knowledge may have been limited to small groups of artisans or priests who failed to pass it on before the Parthian Empire's decline. The artifacts we've examined are physical evidence that disrupts our standard technological timeline. From the Antikythera Mechanism's precision gears to the iron pillar's corrosion resistance, these objects reveal knowledge we've either forgotten or failed to recognize. Egyptian astronomical tools, Roman concrete, Damascus steel, each showcases capabilities that defy their eras. Why did this knowledge vanish? Wars, natural disasters, or the fragility of oral traditions might hold answers. These artifacts remind us that human ingenuity isn't always cumulative. What other mysteries lie hidden, waiting to be uncovered? Share your thoughts below and stay tuned for more revelations in the next section.